So the computing machine is accepting the input and it will be storing inside the machine. And once it got the input based on the instruction, it is processing the information. And after that, the processed result will be outputting through the output device. So these are the things a computing device will be doing. So the input will be accepting, storing inside the system and processing it, and the result will be outputting. After that, what are the different units of functional units of a computer? So there, for the examination point of view, this diagram is expecting. So you should draw this diagram, what was written over here. So the first block is having input output unit. So it is input unit as well as output unit. And that based on what was the definition was telling, you give the input through this way and store the result in the or instruction in the memory unit. Your processor will be accepting that, and the result of that processing will be again storing in this memory, and the result will be taken from there and it will be outputting through the output device. So this is the input output unit complete structure. So this is the complete structure of the functional units of a computer. So input unit, output unit, memory unit, arithmetical logic unit and control unit is included in the processor. After that, we'll see what is each of this. So this diagram you should draw for the examination, and along with that you should elaborate each of this unit. So the what is the first one? First one is the input unit. So it is not about input devices. So the input unit is what it was telling. Input unit accept the information either from a human operator or from any electronic mechanical devices like a keyboard, mouse or any other input device. So the input unit is accepting the input from the input device and giving it into the memory unit. That is the input unit. Similarly, what should be the output unit? What is the work that output unit is doing? It is not related to output devices. That is one point. So output unit we should take the input from the memory or take the result from the memory and it should display to the output device. So what may be the output device? That may be either the monitor or the printer or whatever it is. So what is the work of output unit is doing? It is taking the resultant value of the processing from the memory and it will be outputting to any of the output device. What is the next unit you are having? The next unit is the middle one, that is the memory. So what is this memory unit will be doing? The memory unit will be having, when you are looking into the diagram itself, you can mention that, see that there are two things as included. One is instruction 1, instruction 2, instruction 3, like that instructions, as well as data has mentioned. So it means your memory unit can store instructions as well as data. Data example I already told you. If you are having an instruction, for example, adding two numbers, that two numbers will be your data, and add a comma b or add two numbers, whatever be the 5 comma 6. So whatever that numbers will be the data part of the instruction, and the complete details will be called as then, like add a comma b. That complete thing is called as the instruction. Okay. Next is so that is the memory unit. So memory unit will be storing the information. That information I told in two times. One is instruction and second one is the data part. Okay. Next is the arithmetical and logical unit. So what is the arithmetic and logic unit will do? It will do the processing part of the computer. So it will do either arithmetic operation like addition, subtraction and all, or it will do the logical operation like any of the comparison. Okay. So arithmetical and logical unit, what is mentioned, performs the desired operations on the input information as determined by the instruction in the memory. So that data from the input device, it is already stored in the memory, and so it was taken from the memory and processing, or processing means doing the arithmetical or logical operation on that. And what is the final thing? That is your control unit. So control unit is for what purpose? It is actually monitoring the complete process. When the memory, from when the data will be or instruction will be fetched from the memory to the processor, and when the result should be writing back to the memory, when the input devices should accept the input, read the input from the input device, and to store in the memory. So all those information and what type of data it is getting and whether it is writing to the memory or it is reading from the memory, all those things will be handled by a certain set of control signals by the control unit. Okay, and all those things I already mentioned. We will study all these things in detail in 111 module. So today for the examination, you will get this question. So for that purpose, you should study this diagram along with that the explanation for that. Next, the details of the input device. So again, after drawing that diagram, you should write this also one by one, whatever I am mentioning now. So already I mentioned you what is the input unit is doing. What is the input unit is doing? Accept the input from the input device and store it in the memory. So that is the work the input device or input unit is doing. You see what is it is doing. So this input unit we can also call as an interface. So what is this interface is doing is, see, your keyboard or audio input or what all are the input you are giving from the input devices, that will be formatted in the specific data format. But the way how the data is stored inside the memory, it will be in the form of bits. So you should convert the data format of the keyboard to the format what the system knows, that is in the binary format. So that process will be doing by the input unit. So that is why it is called. You are also hear that different drivers of keyboard drivers. When you are having a new keyboard, you should install the keyboard driver or even mouse. When you are connecting a new mouse or new keyboard to the system, you can see that new driver is installing in the system. What is this driver? That driver is actually the interface. That drivers will be doing what all are the functions. The major function is the input device is formatting the data in a specific format and the computer will be processing the same data in some other data format. So conversion of those two formats, that is a major work your drivers will be doing, or the drivers is also called as an interface circuit of the input device. So that is the interface thing. So there what all are the things? That is with the common sense you can write, accept binary information from the input device, present this binary information in the format expected by the computer, and transfers this information from the input device to either memory or processor. So these 3 points you should write with respect to the input unit. So what all are the things? Accept the binary input and store that input in either memory or processor, and convert the data format of the input device to the machine understandable format or the format what your computer is expecting. Now you read the red lines in the PPT. So that itself will give, if you listen the class, that itself will help you to prepare for your exam. So it is input unit. It will be acting as interface. It is accepting something. What is accepting? Input from the input device. Presenting what? Presenting in the format of the memory and processor. And finally, the data will be transferred. Okay. So this diagram, actually this diagram is coming little late, but for explaining the memory unit, I think this is required. So when we are discussing about processor, in the previous diagram, we were explained only about the control unit and ALU unit. That means all the data, whatever you are having, you were stored in the memory unit. But other than that, there are few other set of memory is already presenting inside the processor. These are some of that one. So mainly we will be calling it as registers. Maybe these words you may hear. What is this registers? How it is differ from the normal memory? The registers are residing inside the processor, so that when the ALU wants to process certain things, those registers data is easily available for your ALU. So if you want to process certain data, actually from the memory you will take that data and it will keep inside the registers. Because the registers are present inside the processor, your ALU can from the take those data from the processor and you can process it. Okay. So that is the advantage of keeping registers inside the processor. So these registers are called as general purpose registers. This is called the general purpose registers. We will discuss about MAR, MDR, PCIR, all are different types of registers. We will discuss in detail in our next class. So only one thing I want to mention you that instead of normal memory system, we will be having a separate memory storage inside the processor also, and that memory we will be calling as registers. There are n number of registers are present inside the processor. Next, so only one unit we have discussed till now, that is our input unit. What is the next unit? Output unit at the end we'll discuss. Next unit is when you are reading an input from the input device, it should store inside the memory. So it should store inside the memory means I should tell about what is this memory unit. Memory unit itself, already we discussed that two types of data will be storing inside the memory. What are the two types of data we are storing inside the memory? Tell me, anyone? What are the two types of data we are storing inside the memory? Two types of information what we are storing inside the memory. Very good. Sanjana? Very, very good. Okay. So the data what we are storing inside the memory are instructions and data. So the information storing inside the memory are instructions and data. And also we told that the data inside the computer system will be storing in terms of bits. It will be storing in bits. So bits means either in terms of 0 or 1, the complete data, even the instruction is also storing and even data will also be storing. Next thing is, see, even though this is looking little extra things, you just, when you are referring the slide, again I am telling you just read the redlined one. That is enough. But when I am explaining, you should listen the complete thing. So what is this thing is telling is the processor reads the instruction and reads or writes data to or from to the memory during the execution of the program. So this is your memory you are having. So from that memory, change the color. From that memory, you should take the data to your ALU for processing. So from the memory, you should take the data and you should store it in the ALU. So when theoretically we were telling the data will be storing in terms of bits or zeros of 1. So that 1 or 0 will be directly transferring to the ALU. But usually it is not transferring as a single 1-bit data. Instead of that, a group of bits together will be taken from memory and giving into the processor or into the ALU unit. And that group of bits together is called as a word. You can see a word. So when a group of bits together is transferring from the memory to the ALU unit, and that group of bits is called as word. And the number of bits present inside a word is called as word length. For example, 4 bits together will be transferring from there to the processor, and that is called as word. So at a time, one word will be transferring from memory to processor, and the number of bits present inside the word is called as word length. So only that are the points. So the data will be storing in form of bits, and the number of bits transferring from the memory to ALU is called as word, and the number of bits present inside a word is called as word length. Okay. Next thing, I want to take certain data from the memory to ALU, and where is that data or instruction is present inside the memory? How can the processor know? In the memory unit where my required data is present in the memory unit, that processor should know. For that, what we are using is we are having an address associated with each of the word. So that if the processor knows that corresponding address, processor can take that data from the memory. So this you can just remember like a story. So there is not much things are required. You can take the data from the memory to ALU, and the data will be transferring in the terms of words, and the number of bits present inside a word is called word length. And where the data has residing inside the memory, that will be processing in terms, it will be accessing through the address. So processor should know the address of that. Okay. Next one. What are the different types of memory present inside the computer system? What are the different types of memory? Already you are familiar with the primary memory and the secondary memory. So the memory what is present inside the system is called primary memory. Primary memory itself is two types: random access memory, RAM and ROM. So RAM is random access memory, ROM is read-only memory. Random access memory means from the memory unit where it will be having so many number of addresses or something. So from there, so this is the memory unit you are having. Every time you will be having lot of addresses, and in each address it was storing the data. Random access memory, at any point it is not sequentially accessing the address one by one. From any point randomly you can take the data. That is the random access memory. And ROM means it is just a read-only memory. So the data you can't edit or you can't update. You can just read the value what is present inside that particular one. So already, what is the secondary memory? Secondary memory is the extra memory you are adding to the system for extra storage. Already you are familiar. All of you are having hard disk and pen drive, all other things. So that are the extra memory you are using to the system. So that is called secondary memory. And also you are knowing about RAM, which is RAM or ROM is a volatile memory. RAM is a volatile memory and ROM is a non-volatile memory. So what should be the content of ROM? Already I told that we can't edit that memory, and it is non-volatile means it will be existing there even if power is switched off. So what should be the content of the ROM? Mostly the operating system will be there. So even if you are switching on the system again, that data you should not lose from the system. So usually the operating system, and even we don't want to edit something on that. So that's why most of the time ROM will be having the operating system related thing. Next one is related to memory only. So what is memory access time? What do you mean by that, memory access time? Who will be accessing your memory? The processor will be accessing your memory. When the processor is accessing the memory, how much time it is required for accessing a particular word from the memory to the processor, and that time is called as memory access time. Okay, so that is the definition was telling. Memory access time is called as access any word location in short of a fixed amount of time based on the address. So from the memory, if we know the processor knows the address, so based on that address, the processor is trying to access a particular instruction. During that time, how much time is required for accessing it? So that is called the memory access time. Next one is telling about how much time it is required for communicating. Already we have we saw that there is a separate memory unit, and there are few set of memory which is already present inside the processor itself. I told you what we are calling that type of memory. What is present inside the processor? Very good. Registers. We will call it as registers. Also, we can call it as cache memory. Cache memory we will study actually in detail. The most cache memory is also present inside your processor. So that cache memory or the registers, that is very near to your processor or ALU unit. So the access time will be less for that corresponding memory, and but the access time for this separate memory unit will be high for the for accessing the content from the separate memory unit will be high compared to the registers or cache memory present inside the processor. That is the content of this slide. So you can see the communication time of cache is less compared to the separate memory block what you are having inside the system. So this is all about memory unit. So what all are the things we have discussed in the memory unit? We were discussed about what is there in the memory unit, how the data will be storing inside the memory unit, how it is transferring to the processor, and what way they are accessing the data. And after that, what are the different types of memory? And after that, we were discussed about what is memory access time and how it is related to different separate memory unit and how it is how fast the data transfer between the registers and processor. So this is what the thing we were discussed. So cache is also a part of the memory which is present inside the processor. So this is all about memory unit. Now we'll move on to the next unit. So that is arithmetic and logic unit. What this arithmetic and logic unit will do? Now the data has read from the input unit stored in the memory. That much part we did. Next is we should process the data what is there in the memory unit. So arithmetic and logic unit will be doing either arithmetical operation or logical operation. What is this arithmetical operation? Addition, subtraction, multiplication and all will be the arithmetical operation. What is the logical operation? Logical comparison, either it is greater or less, logical and or not. So you have studied it in. So that any of the logical operation or arithmetical operation will be performing and by the arithmetical and logical unit. And next thing is telling about where when the arithmetic and logic unit is present where inside the processor. So whether the data actually what is the use of the registers they were trying to tell. The data every time it is accessing from the memory unit to your processor will take a lot of time. So only they have designed a specific registers inside the processor so that your ALU can take the data immediately. So when it wants to process a specific instruction, actually that complete instruction will be taken from the memory unit and it will be storing inside the registers so that the processor can take the data immediately and it can process it. Okay. So that is the thing we'll be doing it. In order to execute an instruction, operands needs to be brought into ALU from the memory. So where will it store? So for storing that, operands will be taken from the main memory to your ALU. So that data will be storing where? Inside the registers. Operands stored in general purpose registers available in ALU. So the two advantages is there. One is easy access and second is access time will be reducing. So access times of general purpose registers are faster than cache and main memory. So it is faster than, so even now three words of types of storage you heard. One is called main memory. Second one you heard about some cache. I told you that is also present inside the processor but away from the ALU. And also we have registers. So most easily accessible thing will be present inside the registers. So registers are much faster than other main memory and cache. Once the processing has done by the ALU, that result again back to store into the memory. If it is immediate, if, for example, 5 plus 7 plus 3 plus 2, so that is having lot of things to do. So the intermediate result is the processor is getting that intermediate result again it won't write to the main memory. Instead of that, that intermediate result will be storing again into the registers only because that addition intermediate result is again needed for further computation. So for that purpose, actually the registers will be storing that data. But once the complete calculation has got over, the result will be again writing back to the main memory. Why? Because the output unit is having only access to the main memory. Okay. So it will be writing the complete results. That is what written. The results of operations are stored back to the main memory or it is retained in the processor for immediate use. Immediate result of the processing will be storing in the registers and all other results will be storing back into the main memory once it completes the computation. So that's all about ALU unit. So things are It is doing for arithmetical and logical operation, and the result operands will be taken from the main memory and storing in the register, and the result of the calculation or computation will be storing inside the memory. And last one is our control unit. Already we have seen this. These are the operations of the thing. Accept the input, that is input unit will be doing. Storing it, memory unit will be doing. Processing it, ALU unit will be doing. And provides output, that is actually output unit will be doing. And we didn't explain it. So what is this control unit will be doing? I already told you, control unit will be doing the coordination part actually. Operations of input unit, memory unit, ALU unit, and the output unit are coordinated by the control unit. So what do you mean by that coordination? When and what to do. That is the thing coordination means. So instruction controller, what operation should take place, whether it is storing the results to somewhere, whether it is processing something, or whether it is transferring from memory unit to processor or processor to memory unit, or what are the operation it should do. That is the first coordination thing as controlled by the control unit. Second thing is when it should perform. So what and when will be decided by the control unit. When it performs, control unit generate the timing signals. All these things will be doing through the certain set of signals that we will see in the fifth module. So that will be generated through a control signals, and then control unit will generate the timing signals and determine when a particular operation should take place. Okay. So finally we reached our output unit. What is the function of the output unit? Output unit is mentioning like not any output device, like input unit what I told. That is the same thing even output unit is doing. Either it is taking the input from the information in the memory unit, the processed result from the memory unit, and that is in the computer compatible format, in the number of bits format. That will be transferring to the output device into and converting the data from the computer compatible format to the output device compatible format. That was the work done by the output unit, or it is also called as output interface. So that is one, the interface of the thing. So it is accept the results of provided by the computer in the binary form, and what is doing? Convert the information in the binary form to the form understood by the output device, and it is transferring the data. So this is what the things your output unit is doing. So the only one thing we are discussed in today's class, this much only even I am teaching it. Okay. We'll discuss the next thing is about bus structure. So complete that first question's answer is completed. What are the different units? So the first block diagram, after that each of this unit and whatever the red line things I have mentioned in the slides is mandatorily should be there in your paper. I will share the slides as well as the recorded sessions video link in the Google Classroom. Last class things I have already posted in the Google Classroom. So bus structure. So what is the use of the bus? A bus will be taking people from one place to another. So even here also, we be having a set of connecting wires that will be connecting different functional units. What are the different functional units that we already studied? Input unit, output unit, memory, processor or arithmetic logic unit, and control unit. So these units should be having a connection between them, and that connection should be happening through a bus structure. So normal bus we know that also will take passengers from one place to another. In the same way, even data will be transferring from one functional unit to another functional unit through a set of wires, and that wires structure is called as bus structure. So you can see there are many times to connect different parts inside the computer. Read only the red line, that itself will give you the clear idea. Connect parts inside the computer. Group of lines connecting path devices, a bus. So the different lines will be connecting, and it is making a bus. And next point is completely new. Instead of what all are the data things you can carry inside the bus, or what all are the things already I told, the data what is present inside the memory will be taken to the processor. So data part we should transfer. What other thing I told, when you want to access a specific data or instruction from the memory, the processor should know the address. The processor should tell the address to the memory unit. So the address is one component the processor should transfer to the memory unit. So the bus structure should also transfer an address. And also I told there is a control signal technique. Control unit will be performing that work, that is through a set of signals, and that signals should also transfer from one unit to another. So these are the things the bus will be carrying. We will be having, if you think like a vehicle, it will be carrying maybe goods or services or even people or what all other things. In the same way, whatever the bus we are having inside the computing system, it is having to transfer three different things. One is address, one is data, and one is control signal. Okay. So this is a single bus structure. So you can see the input device is connecting, and then this is the complete one single bus. This is a set of lines. So that will be input device is connecting to this. That result should store where? It should store in the memory. And once it has stored in the memory, from memory, the processor should take the data. And once this has happened, then the processor should write the calculated result in the memory, and then from the memory that output unit is taken the data and it is displaying to the user. So this is the complete thing. So in that, actually this common bus will be used by many times. But what is the drawback of the single bus structure? At a time only one transfer is possible, either from input device to the memory, or it may be from the memory to processor, because the bus is common for all the units. So only, at a time only one transfer is possible in the single bus structure. What are one more problem for this structure is, maybe the common bus is connected with the different devices. So few devices will be really slow and few will be really fast. For example, the processor is very fast compared to the input devices. So but still the processor should wait if the input device is connected to the bus. So what is the thing? How can we solve that issue? I think you understood what is the problem. We are having only one common bus, and different units are connected to it. In this itself, processor and memory is faster compared to your input unit and output unit. But if the input is transferring a data to the memory, the bus is not available for processor for doing any other thing. So processor should simply waste its time for completing this first set of transfer from the input device to the memory. So we are wasting the time of our processing speed of the processor. So what is the extra thing we can do is, we can keep a buffer over here. From the input device to the bus, we can keep a buffer. So what is buffer means? It is a small storage area. So what is it can do is, it can read the input from the user and store it inside the buffer. So once the buffer is full, then immediately that all data can be transferred into the bus, and it can directly transfer to the memory. Otherwise, reading the input from the user and putting it into the bus structure will be taking time. So that reading process should happen before, and the result will be storing inside a buffer. Okay, we'll see that slide. That is the issues. You can see I have written it. The devices connected to the bus vary widely in their speed. For example, some devices are relatively slow, like printer and keyboard, but some other devices are relatively fast, like optical disc, and memory and processor are fastest device of the computer. And we know that at a time only one transfer is happening through the device. So what is the thing we can do? So how can the speed of the bus will be depending on the slowest device which is connected to the bus. So how can you solve this problem? You can use a separate buffer. There you read the input and store it in the buffer. Once the buffer is full, complete data you can transfer through the bus. Okay, this is all about our today's session. So two things we have studied. We have studied two things. One is, what are the different functional units of a computer. After that, we were discussed about what you mean by a bus structure, a single bus structure. This diagram is also important. This diagram is also important. What is a single bus structure? After that, what are the drawbacks of this single bus structure? How can you solve it? So that is the things for today's session. Okay. And what we will discuss in tomorrow's session is till now we were discussed about what are the different functional units of a computer, how it is interconnected. A little bit idea you got it. Tomorrow what we are trying to do is you have an instruction in the memory and you are trying to execute that complete instruction in the processor. So what are the steps involved in it? That is what we will be discussing in our next session. Okay. So this is all about today's session. Now, C section, no, 164. 164 can ask one question. USN 164. Don't leave the meeting. Even if you didn't answer, also nothing will happen. It is just any, or even or one student can give a conclusion regarding what all things we have discussed. Both are fine. Any one student, if you can tell that what all things we have discussed in the class, if any one student can tell also, it's fine. No need for asking questions in the chain way. So it means that nobody has listened anything in the class. Just overview. I don't want the complete details what I have explained. What all things I have explained in today's class.
Ma'am, can I try?
Yes, of course.
Today we began with few basic points, like from the beginning, like what is a computer and definitions, a few points for it, like accepting, storing,
Okay, okay, fine.
providing processing.
Then,
Then we discussed about the functional units. Uh, it has a diagram,
mm,
input, memory,
mm,
processing and output.
mm.
Then
Control unit.
uh, uh, input, output, all those units were explained.
After that, I explained
After
about
that, structures,
that connecting thing I told. What is it called? How
connecting
different
thing.
functional units will be connecting. It is called bus structure. Bus.
Okay.
Ah, okay, very good. Okay, fine. So, your USN, you tell me?
146.
146. So, next day, any other person can explain. 146, I have noted down. Okay, fine. Other things,
Thank you.
I got some 56 people's details. I will take one more time attendance and I will share it with you. Mm, I was trying to get your details. This is from 56 only. Okay, before that, I will show you one more thing. I think what's the time? Okay, time is there. Okay, this is just a video. The video was just telling you something. You just listen.
Comes down to ones and zeros. You've most likely heard that this code of ones and zeros is what's referred to as binary. And while almost everybody knows that this is somehow related to what computers do, very few of us seem to understand what binary is or why computers use it. If you want to know, then this video is for you, because it's actually a very simple concept and still quite fascinating. Before we get to computers, let's talk about what binary itself is, as it existed long before computers did. Binary is nothing more than a system of counting. To understand how it works, let's look at two other systems of counting, tally marks and the glorious base 10 positional that we all know and love today. Tally marks are the simplest counting system imaginable. However many things you have, you put down that many marks, easy as pie, but not very efficient. Meanwhile, base 10 positional, which is what we use today, uses a different symbol to represent different amounts of things. With the numbers 0 through 9, we can recognize that each symbol indicates a different amount of things. If we need to represent something higher than 9, we add a digit to the left, roll this first digit back to 0, and start over. This system is very efficient compared to tally marks because each digit we add exponentially increases the amount of things we can represent. Because in this system we add a new digit every 10 things, each digit represents an increasing power of 10. This is the number of ones we have, the number of tens, the number of hundreds, the number of thousands, and so on. Now this is probably something you already know, but it's very important to keep it in mind when we talk about binary. Now binary works the exact same way as base 10 positional, but instead of each digit going from 0 to 9, it goes from 0 to 1. Counting upwards in binary sounds like this: 0, 1, 10, 11, 100, 101, 110, 111, and 1000. Because each digit of binary has only 2 values and not 10, additional digit represents an increasing power of 2 rather than an increasing power of 10. So this is the number of ones we have, the number of 2s, 4s, 8s, 16s, 32s, 64s, 128s, and so on. Not nearly as efficient as base 10, but exponentially more efficient than tally marks. Literally. So now that we know how binary works, let's talk about computers. Why did the first computer creators, as wise and intelligent as they are, waste their time with such an ineffective system of counting? Well, it's because of a physical limitation on how computers work. Everything a computer does comes down to what's known as microtransistors. Simple, tiny, eensy-beensy little switches that can either be on or off and can be flipped on or off with a very weak electrical charge. The first goal was to get computers to count. And to get them to count by using these switches, we could use the tally system, meaning the number of on switches equals the number of things we have, or we could use the much more efficient system of binary, where each switch represents a digit of binary. 8 transistors using the tally system could represent a number as large as 8 by turning all of them on. With binary, we can represent a number as high as 255. An on switch means a 1, and an off switch means a 0. Now is a good time to mention that a single transistor is what's known as a bit, which stands for binary digit. A byte is 8 of these bits in a row, which means any number between 0 and 255. So if binary is just a system of counting, what do people mean when they explain how to spell things in binary? Well, what they really mean is how to spell things with ASCII. The American Standard Code for Information Interchange is a way to convert a computer's data, which can only be in numbers, and turn it into letters for humans to have an easier time to work with. ASCII simply assigns a character to each value represented by a byte of binary. And because a byte has 8 digits of binary to work with, and 8 digits of binary can represent up to 255 values, ASCII had 255 letters and symbols to choose from, more than enough for the entire alphabet, punctuation marks, and other symbols. For example, the corresponding ASCII number for an uppercase A is 65. Now, 65 in base 10 is equal to 1,000,001 in binary. So whenever you type in an uppercase A in a word program, a coding program, or a scripting program, or whatever, somewhere there's a little tiny row of 8 transistors arranged in the pattern of off, on, off, 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 on, which represents 0, 1, 0, 0, 0, 0, 0, 1 in binary, which is interpreted as 65 in base 10, which is converted by ASCII into an uppercase A. You're likely starting to get a feel for the staggering amount of transistors required to write something as simple as a Facebook status, let alone.
Okay, your patience also I should consider. I have already taken your attendance. Um, you can watch the video whenever you are free. It's fine. Okay, you can leave. I have already taken your attendance from the screen. Okay. 61 people have joined. Thank you for joining. Let's see. In today's class, what we are discussing is different basic input-output operations. How we will be looking into little more detail. Actually, we will have the second module completely regarding this input-output unit operations only. But little more details of the most basic input-output operations we are just discussing. And we'll move into the first one. What it is trying to tell is the data on which the instructions operate is not necessarily already stored in the memory. So this is the structure you are having. So it is not always maybe the data will be present in the memory. Till now what we have discussed is from the memory unit the processor has taking the data. But it's not mandatory that always your data will be present in the memory. Maybe that data you can give from the user also, like in from the input device or how you are typing in the keyboard. In the same way, the data may be taken from the keyboard and that will be directly taken into the processor. So that is one more way for getting the data for the processor. So it is not always mandatory that your data should be either in the processor register or it in the memory. Instead of that, it may be coming into from the input device. So in that time, what is the problem? Already we have discussed input devices will be or output devices will be very slow compared to the processor speed. So there will be a mismatch in the data transfer rate. So there is a need for synchronizing this input device with the processor speed. So when I was explaining this in the first module itself, I told for that they will be keeping a buffer, a small storage area between this input device and processor. So processor will be, input device will be keeping the data in the buffer or in the small storage area. And from that storage area directly, when that storage area is full, the processor will be taking the data directly. So uh, that was the overview I have given to you. We will discuss little more uh, in details regarding this operation, what all are the registers involving in that, how that is happening. That is a little more details we'll be discussing in today's session. So data need to be transferred between processor and outside world. That may be from the keyboard, any of the input device, or even from the disk, it is reading the data directly. So I/O operations are essential. The way they are performed have a significant effect on the performance of a computer. So only one thing you should know from this slide is from the input device also processor is taking data directly. So how it is doing, we are just seeing. Then what is meant by program controlled I/O? So what is the meaning of program controlled I/O? If the program inside a CPU monitors the status registers, for that I/O transfer, it is called a program controlled I/O. That means there is a program which will be present inside the processor, and based on that processor, that program's instruction, based on that program's program will be executing inside the processor. Based on that, the actions will be performing. What action? From the input device, the data will be transferring to the processor. In the same way, from the processor, the result will be transferring directly to the output device. And that will be monitored by a program in the CPU or program in the processor, and that is called program controlled I/O. So what are the I/O operations example? Read a character input from the keyboard. Or I already told, so that will be taken from the keyboard to the processor, and then similarly produce a character output on the display screen. So whatever for example, I am pressing A from the keyboard, that A is visible on the screen. So how that data transfer is possible? That is what, if I am typing in a word A, I have typed from the keyboard, that A is visible on the screen. How that is possible, we are discussing in this session. So already I told the difference in speed between the processor and I/O device will be making synchronizing the data transfer between this operation, because the speed of processor will be high. The I/O devices, input output devices will be working very slow compared to the processor speed. So the data transfer rate may be 1 billion data bits will be processing by the processor in 1 millisecond. The input output devices will be transferring only 1000 bytes of data, so 1000 bits of data. So in that time, that speed mismatch will be there. So processor should wait until it should get the data from the input device. So that in that case, a synchronization between these devices is required. What is one solution they have developed is, first processor will be sending the first character. It is just telling about with respect to the output device. First processor is having a value, that is A, that I have given from my keyboard, that was stored in the processor registers, and from there it is trying to transfer into the output device. How it will be transferring? The one scheme of doing this, because of the speed mismatch, what was the thing it was doing is, processor will be sending that first character to the output device and waiting a signal from the output device that it has received that first signal. Then if the processor was getting an signal back from the output device, it will be sending the second character. So that was one way, that is like an acknowledgement scheme. So first character it will be sending into the output device. Output device will be giving a signal like it has already got the first character. Then it will acknowledge back into the processor that it received it. Then the processor will send the second character. So that way it was proceeding, but still it will be having a loss of processor speed, and it will affect the processor efficiency. So we are coming with a buffer scheme. This is what I have told you. So you can see this is the input device you are having. I am assuming that the input device is the keyboard. This diagram is important. This is the only thing I am telling now. Till now, only one point you should remember, that is the data will be taken from the input device to the processor, or even the processed result can be sent from the processor to the output device. The devices will have a speed mismatch, so that we need to find out certain synchronization schemes. So this is the result of that synchronization scheme. So we'll see, this is the input device what we are having, the keyboard, and the display device want to display. So here I am to type the character A from the keyboard, I want to display that character in the display device. Please listen. This is only 5 minutes you listen. That is enough for this thing. You just understand. So I told a buffer will be there. That is a small storage area will be present along with your input device. And that is called data in register. For input, there is a small buffer or small storage area along with any input device, and that small storage area is called data in, or that is the register for storing the device input what I am giving from the keyboard. Along with that, it will be having a 1-bit location. Already you will studied about flags, zero flag, and all those time I was telling like it is a 1-bit location. So similarly, along with your input device, one storage area will be there, that is called the buffer, and that for corresponding to input device, the buffer name is data in. And other than that, 1-bit location is also there, that will be working like a flag. So it can take only 1 bit of location, either it will be 1 or it will be 0. So processor, instead of checking how processor will get to know that whether data in register is full or not, instead of transferring the first character from here to here, it will be taking time. So what it was doing is from the keyboard device, it will be keeping all the data in the data in register. Once data in register is full, what will happen is once data in register is full, your SIN will be updated to 1. So SIN is the flag which is associated with the input device. So once the data in register is full, then the flag will be set to 1. So instead of check how processor can check that whether the data in register is full or not, processor will directly check what is the status of SIN flag. If SIN flag is 1, that means from the input device it has read the input and it was stored in the data in register, and data in register is full. So that time your SIN will be having value 0. If processor is again coming and checking that what is the value of SIN, and if SIN value is 0, it means that no, still your data in register is not full. So processor can use for some other uses. Processor time can be used for other purpose. So that is what the processor working, and with respect to the input device things. So only 2 registers. One register will be associated with the input device, that is called a data in register, and one flag is there. So these register and flag together will make the device interface. This registers and flag that will be together with the together will make a device interface. So I was telling about the drivers. So keyboard driver or keyboard interface. That means mainly the components are, one is data in register and one is the SIN flag. So when from the keyboard, if the data was reading into the data in register and SIN flag is set to 1, that means your data in register is completely filled. That time the complete data from the data in register will be moving from data in register to your processor. That processor where you can store the data. Inside the processor we will have storage area. What we will be called that storage area? What we can call the storage area inside the processor?
Cache.
Cache memory is there, registers are there. So inside the register or general purpose register, we have studied about different registers. So once that complete data was filled in the data in register, that data will be completely transferring from the data in register to the registers what is present inside the processor. So that is all about input device. So when you press A, that A will be coming into the data in register. And once the data in register is full, if assume that your data in register is having only 8 bits of storage. So that time when you are pressing the first character itself, your data in register will be directly coming to data in register. So that time itself, your when first character A is filled in data in register itself, your data in register is full because one character will be taking 8 bits. So immediately your SIN register will be, or SIN flag will be set to 1. So that will be taken directly to the processor register. That will be with respect to the input device. In the similar way, what is this data out register, a data out buffer, and S out? So this is the flag and this is the register. So this is the register you are having in the output device. Similar to this is the flag you are having. Similar to your input device, you will be having the output device also. So when transferring the data from the processor to the output device, that will be because the processing speed of the output device will be slow. So what it will be doing is processor will send all the data to the output device, and output device means into the data out register, and it will be from that is the only thing processor will do. Then from the data output register to your display device, how that transfer will be happening, that is will be doing internally inside the display device. So what is the S out, when this S out flag will be set and when this S out flag will be reset? When your display device is ready for displaying a character or the data, displaying the data, that time your S out will be set to 1. What is this S out status is telling? When the display device is ready to display the data, that time your S out will be keeping the value 1. If the display device is already busy for displaying some other characters, that time your S out value will be 0. So when the display device is ready for displaying the character, that time S out will be 1. And processor, similar to input device, processor won't check what is the content of data out and all. Processor will just check what is the status of S out. If processor was find out that S out is 1, that means the display device is ready for displaying the thing. So that time, whatever the data processor wants to display to the display device will be taken and it will be storing into the data out register. So this is the complete working of the display device. So in the input device, you will be having one register called data in, and SIN is the flag associated with it. Both together, register and flag together will be calling as a device interface. In the display device, you will be having similar to data in, you will be having a register called data out, and similar to SIN flags, you will be having an S out flag. When you are inputting the data from the keyboard, that will be storing in the data in register. Once data in register is full, your SIN flag will be set to 1. Processor will check the status of SIN flag. When SIN flag is 1, that time from the data in register, the data will be taken and it will be storing in the processor. In the second case, when the display device is ready for displaying the content, S out flag will be set to 1. So processor will be checking the status of S out flag. If S out flag is 1, that means the device is ready for displaying. That time the data whatever processor wants to display in the display device will be taken from the processor and storing in the data out register. This is the complete working of the program controlled IO. So the same thing as an instruction it was written. You can see if SN is equal to 0, what is the thing? If SN is having the value 0, what is the thing it should do? Processor should wait, correct? Because it was telling like your data in register is not full. When SN is having value 1, then the data transfer will be happening. That means the buffer will be full so that it will be transferring from the data in register to the processor register. That has written like read wait is just a label. It is just an address, or you can read wait, any name you can give, that is just like a variable name. Read wait branch to read wait means again and again, if this condition satisfies, it will be coming back to read wait only. So it means that if SN is equal to 0, SN is equal to 0 means your data in register is not full. So that time the processor should wait. So what will happen? Branch to read wait means if SN is equal to 0, again it is coming to this statement. And again branch to read wait if SN equal to 0. Again processor will be checking what is the value of SN. That time again it is 0. Again it is coming into the same statement. Repeatedly it is checking the same if SN value is 0, repeatedly the same set of instruction or same set of statement will be executing. Otherwise, if Sn is equal to 1, that is the next statement. Otherwise, the complete that loop itself, it will be executing. It is like you will be having a while loop condition. You will be while 1 then semicolon if you put means that will be continuously executing in that statement itself. So that similarly, if that statement, it means that if branch to read wait, if Sn is equal to 0, it means Sn is equal to 0 means always the same statement is executing. Again, it is branching to read wait. Read wait is the statement itself. Otherwise, what should happen? That means Sn is having the value 1 means the data transfer should happen. That means your data in register is full. Transfer it from data in register to processor. So processor register is R1, that you know. So that from the data in register to R1 data transfer will happen. Similarly for write also, what will happen? If S out is equal to 0, that means the display device is not ready. That time again and again S out is equal to 0, display device is not ready. So again and again it is coming into write wait thing, right branch to write wait. So that again and again the same statement will be executing until S out value becomes 1. If S out value becomes 1, then what will be the data should transfer? From the processor, the data will be transferring to a data out register. From the processor means that is your R1 register. From R1 to data out, data transfer is happening. It is not mandatory that you should write a read wait. You can write simply wait or anything. Any name you can give, but the same name you should write here also. Okay, next is actually this data in and SIN register where it will be storing. So that is even though it is a memory, so the corresponding to that memory, there will be a separate memory will be allocating, a special memory will be allocating, or you can even allocate a memory block inside the memory unit itself. So that is called a memory mapped IO. This is also the some other way the same set of statement has written. You can read wait test bit. It is in a status bit instead of checking S in value. You will be having an input status register. It's the third which will be deciding the SIN. It's not required, but it is there in the syllabus textbook, so I was just included. So SIN is the third bit in the status register. What is status register? When I was explaining the conditional code flag, I told there will be a register which will be having only flags as its content. So first one is a zero flag, second one is a overflow flag, third one is the SIN register is our assumption. So third bit is the SIN register of your status flag. Status flag means only the flags which will be stored as a content inside a register, that is called status flag. So what is the thing it is taking? If SIN third bit in the status flag will be checking, that is SIN value. If branch 0 means if this SN is equal to 0, branch will be 0. In that case, again it is going to read wait function. Otherwise, this is the register. This register is called as input status register. That is the meaning of in status. Just one variable. I think you can write even some other variable also. It's not mandatory. In status is the name of the status register you are having in the input device. So I told each bit, each location will be storing one or other set of flags. Maybe next one will be the negative flag. Next one will be the carry flag. So this is the total flag structure I am having, that as a register I am stored. So that in that third bit will be representing your SIN value. So it means that test third bit of the status register, that is your SIN bit. If that bit is equal to 0, automatically branch will be 0. So branch is equal to 0 means again that means your input buffer is not full. So you should call again read wait function. Otherwise, you can just move the content from the data in register to R1. This is not important, but this is important. These two you should study. That will be actually what is the explanation I have given over here. That is same thing as an instruction has written over here. So here you can see what is the drawback of this. Again and again the processor should check what is the, you can see two continuous looping structures we were using. See, here also you are having a wait until your SIN is set to 1, you should wait. That is one wait in the reading process. And similarly, in the writing process also, processor should wait until your S out will be equal to 1. So that is the two waiting loops will be present inside the this current scheme. So for alternative solution is the interrupt. So with a given priority, we can insert interrupt into the processor so that it will stop. Already the interrupt concept I was introduced to you. So it was like when whatever the processor is doing, that work will be stopped and it is doing the most priority work what processor wants to do. So that is called interrupt. So that is one way for solving this issue. Here also we will have two set of waits from the processor side, one for making the SIN flag to 1 and the other one is S out to be 1. So that problem can be avoided through an interrupt. Okay, stacks we'll discuss in the next class. In today's session, we are discussing about how an instruction is executing inside the system, or which all are the registers or which all are the paths that instruction is going through inside the processor and from the input unit to the complete execution. So that is what we are discussing. So first of all, what do you mean by an instruction? The instruction is a command we are giving to the processor for doing a specific task. So what all are the types of tasks and processor is doing for us? The processor is doing mainly three types of tasks. One is data transfer, that is within the computer. That means within the computer already we know about the different functional units of a computer. So it may be from any two internal functional units inside the computer. That may be either memory to ALU or maybe from the input unit to memory, or maybe it will be from the memory to ALU or ALU to memory. So whatever it is, that is one is data transfer within the computer, and second one is from the input device to computer. That is like whatever I am typing in the keyboard or whatever I am giving through the voice command or whatever I am giving through mouse. So that is from an external world, it is giving input to the computing system. That is the second type of data transfer. And third one, as you know, it is arithmetical and logical operations. So these are the type of instructions present inside the system, and that will be, these are the works the processor will be doing for us. So three types of instructions are there. We will discuss in the types of instructions and all minute details later. Now an overall idea only will be giving. So three types of instructions are there. So that you know what is a program. Program is a sequence of instructions for performing a specific task. And where these instructions will be storing? Already when we discussed about the structure of memory, we have discussed that, okay, two types of things will be storing in memory. One is instruction and second one is data. So our instructions, a set of instructions, what is there in the program, that complete instruction will be storing inside the memory. So whenever the processor wants a particular instruction to execute, processor will give the address of that corresponding instruction to memory unit, and then it is reading that corresponding instruction from the memory unit, and that will be executing by ALU. So the processor will be reading that instruction from the memory is also called as fetching the instruction. Both are same. Reading the instruction from the memory is also called as fetching the instruction. So processor fetches that instruction and make up the program from the memory, and then it is processing that corresponding instruction. So this is the basic steps involving, and when we have discussed about the structure of the processor, we were showing about a lot of other registers. Now we will see what is the relevance of those registers and where we are using it. Now, how a typical instruction will look like. Here we are in the complete syllabus, we are discussing only about assembly level programming language, not about the programming language what you are familiar. So it is all about assembly level programming language. See, this is an example of assembly level programming language. You understood what is this instruction is doing? So every instruction will be having two different parts. It was written like add location A. Loc A is representing location A. So that is just an address, comma R0. R0 is what? When we discussed about the structure of the processor, we were mentioned that there are a lot of memory units which are residing inside the processor. That type of memory is called as registers. So R0 is one of the general purpose registers. You will be having n number of registers present in the processor, and R0 is one of the register present inside the processor. So add location A, R0 is an instruction, and that instruction will be having, every instruction will be having two different parts. One is opcode and second one is operand. Opcode means what is the operation it is asking the instruction to do. The instruction or operation is addition. So opcode is add. And what is the operands? What all are the operands or data present in the inside the instruction? That is the location A and R0. So location A is one address like 2000, 3000 some address. So the content inside that 2000 is one operand and content inside R0 is another operand. So every instruction will be having two parts. One is operand and another one is opcode. Opcode is mentioning like what operation the instruction is performing, and the second operand will be telling where that operation is performing. Okay. Next thing is actually what this instruction will do. That is what the thing. What if I execute this corresponding instruction, add location A, R0, what exactly this instruction will do? The instruction will be doing a task. Anyway, it is addition that I understood. And the location A, I already told you, certain content will be there in my location A. And after that, I am checking what is the content of R0. Again, one more R0 is there. Okay. And I should take the data present or in both the memory location, and I should add that much I understood. But where I will store it, the resultant value of this one, whether I am storing in location A or R0. The instruction is like you add location A content and R0, and the result you should store in R0. The result you should store in R0. This is what this corresponding instruction is doing. So location A content will be added with R0 and the result will be storing into R0. So whatever be the initial value of location A, assuming that it was 10 and this was 20. So after executing the instruction, location A content will be preserved, that is not changing, but R0 content will be changing to 20 plus 10, 30. So the R0 content will be changing to 30 and location A content will be preserving, and it is performing the addition operation. So that is what the thing I have mentioned. The square bracket is representing the content. So it was mentioning like the content inside the location A, and what is square bracket of R0 is indicating the content inside R0. Both will be added and the result will be storing into R0. Clear? Okay. What all are the difficult things for the processor anyway? Who will perform the add operation? Who will perform the add operation? At the end I will ask a question, so please listen. Add operation will be performing by the processor. So processor will be having, processor can access the data which is residing in R0 immediately, because the processor is already, the data residing in the R0, because see, this is the ALU is performing the data. So whatever the data present in R0, ALU can take immediately. But whatever the data present in this memory, that is difficult for processor to take it all the time. So what it will do is, it will first take the memory things, that is location A content. I told it is some address. So example, it is 2000. From 2000, that corresponding data will be taken and it will be storing in R1 register. And so one operand will be available in R1 and second operand already it is present in R0. So both R1 and R0 is easily accessible for ALU. So it will take the data from R0 and R1 and it will process the result, and the result will be writing back to R0. So even though it was written as a single statement, this location A loading part, that means it is an external memory. It is the internal memory what was present inside the system but not inside the processor. So those data from the memory unit to processor, that transfer is happening through the instruction load location A, R1. So what is happening? Load is the instruction which was taking the content of location A and it will be keeping in R1. My ALU can take the data from R1 and R0 immediately because it is present inside the processor. So R1 and R2 ALU can take immediately. So what I am doing, from location A, the content will be transferring to R1, and then R1 and R0 has processed in the ALU and the result will be writing into R0. Whose content will be overwritten? That is whether R1 or R0 or location A. When I am executing this instruction, add location A, R0, whose content will be overwriting? Whose content will be overwriting? Hello?
Ma'am,
Hello?
R0.
Correct. The content of R0 will be overwriting. Okay, that is the details regarding the typical instruction. Then we'll move on to the next part. So this is the complete structure of the processor. Already you know that memory unit is outside the processor, and other than that, inside the processor you are having different registers like MAR, MDR, PC, IR, and the general purpose registers, ALU, and control unit. This diagram so many times you have seen, but again, this is very, very important. You should study this diagram. So already you familiar with this memory and this general purpose registers that I already told you, where you can already take the data from there. So this is called a general purpose registers. So for every, I told intermediate result and all, ALU can store in the register. So that is for all the operands will be available in the register. So immediately ALU can take that. Control unit also we have discussed, and ALU also we have discussed. Now we should discuss about the other registers present inside the processor. So we'll see what all are the other registers and where we can use these registers. So the registers are, one is IR. IR is representing, it is very, very important. All of you please listen. IR register is instruction register. IR register is instruction register. That you should remember also. IR register, don't give any other expansion. Usually I am seeing on paper like some other expansion you will be writing. Instruction register is IR. Then PC is representing the program counter. Then R0 to Rn-1 n general purpose registers are there. And after that, MAR is representing memory address register. So MDR is representing, next is MDR is representing memory data register. So these are the expansion. So MAR is representing memory address register. So it is a register, and what will be the content of that register? MAR, definitely it will be an address. So MDR is representing memory data register. What will be the content of that? That will be data. And other than that, you can have a general purpose register for storing the operands. And next is program counter. Counter means what? Counting the number of instructions. So program counter is actually a register which will be storing the address of the next instruction to be executed, which will be the next instruction immediately. If the current instruction is processing is over, which is the next instruction the processor should take, and that instruction's address will be storing in the program counter. Are you clear? Program counter means the address of the next instruction will be storing inside the program counter. So we have studied about two registers. One is program counter and a memory address register. Both will be storing an address. That part at least you should remember. So which all are the registers will be storing address? One is program counter and the second one is memory address register. And the next one is instruction register. So instruction register is representing like a, what is the use of this instruction register? Instruction register is, anyway, it is a register, and what will be the content inside that? The currently executing instruction will be the content of the instruction register. So what is this IR? IR is representing instruction register. So what is the content of IR? That is the currently executing instruction will be storing in IR. What is program counter? Program counter will be address of the next instruction to be executed. MAR is what? The memory address register. It is keeping an address. And what is MDR? MDR is the memory data register which you will be keeping the data part needed for ALU. And even you are having different general purpose registers of n number general purpose registers is there that will be storing the operands. Okay, so that are the registers present inside the processor. USN 168. What are the different registers present inside the processor? Tell me. USN 168. (168) is absent then. 169.
Yes, ma'am.
Tell me what all are the registers present inside the processor?
Instruction register, program counter, general purpose register, memory address register, and memory data register.
Okay, fine. So what all are the registers? 170. What all are the registers which will be storing address as a content inside the register? USN 170.
Program counter and memory address register.
Very good. Okay. Okay, we'll proceed. So these are the registers present inside the memory, and I told you what are the purpose of these registers. Okay. Next thing is, again that same thing only has written. You can, if whoever was not listened to the session, please listen now at least. Two registers will be there. So one is called a MAR, that is called memory address register, and memory data register. So memory address register is keeping address and memory data register is keeping data. So MAR holds the address and MDR holds the data. Instruction register holds the instruction that is currently being executed. So currently executing instruction will be storing in the instruction register. What is program counter? Points to the address. It is pointing to an address of the next instruction that is to be fetched from the memory. So program counter is having an address of the next instruction that is to be fetched from the memory. So these are the registers present. Now we'll see the flow of execution of the instruction. So now we'll see the flow of execution of the instruction. Okay, I will show the slide after the explanation. So first, anyway, where will be our instruction now? We will be keeping the program where it will be keeping inside that. It is present in the memory unit. It is present in the memory unit. We know that it is having a memory unit, and from that memory unit, the instruction should come to your ALU. So this is the memory unit. So this is the memory unit. From the memory unit, the instruction should come to ALU. But before that, the ALU should tell to the processor memory unit that where is the instruction is residing. How ALU will be or processor will be giving the instruction to the memory unit? It will tell the address of the instruction. It will tell the address of the instruction where it was present in the memory. So it will be, for example, it is giving a 2000 as the address. So that address has transferred from where to where? 2000 is the address that will be transferring from the processor to memory unit, so that memory unit will fetch that corresponding instruction and it will be transferring to ALU for execution. So that is the complete overview. So we'll try to see what all are the steps involved. So already we are assuming that the input has given from the input device and it is stored in the memory. So your instruction is already stored in the memory. Now from memory to processor, how it is taken and how the result of the processing result will be storing again back to the memory. That is the instruction operating steps we are discussing now. So in the beginning, the data or instruction is present in the memory. Next, initially your program counter. What is program counter? Which is the next instruction the processor should execute? That will be decided by whom? The program counter register. So initially your program counter will be starting with the address of the first instruction. So program counter is initially will be having a value that is 2000. That was the initial starting address of the program. So that will be the content of your program counter. So program counter is having 2000 as the address. So program counter is keeping the first instruction's address into it in the beginning. After that, after execution of the first instruction, the program counter will be increasing to the next immediate value, that is 2000. If one instruction is taking 4 bytes, it will be incrementing to 2004, or one instruction is taking 1 byte, then it is increasing to 2001. So that details we'll see. Anyway, it will move to the next instruction. That much you should understand. So in the beginning, program counter is having the address of the first instruction of your program. After that, what will happen? The contents of this flow, you should remember, the contents of program counter will be transferred to MAR. I told 2 registers will also keeping which one? Address only will it be keeping. So which is the instruction the processor should execute that was initially present in program counter. Now that value will be transferred to MAR. MAR is memory address register. So it is transferring to memory address register. That is the first flow. So initially program was there in the memory. Your first instruction's address is stored in the program counter and that address is transferred to MAR, that is the memory address register. After that, what will happen? After that, whether into that corresponding memory, for example, 2000 is the memory you are having. Into that memory, whether I should write some content or whether I should read the content of that corresponding memory. That information who will provide? What is the operation I should do and when it should perform? Which unit will be giving that instruction? Which functional unit will be giving the instruction for controlling
Control
what?
unit.
Very good. Control unit will be giving the instruction for reading the instruction or writing into the instruction. So once the address is loaded in MAR, the control unit will give a read signal so that what is the next thing it should happen? It should read that corresponding thing. So that is the next thing. So once the program counter content is transferred to MAR, the control signal will generate a read signal and it will send to memory. So that memory unit will get to know that, okay, this is the value, whatever is residing in 2000 or what is the content of MAR, that corresponding address value I should give to processor. And first instruction is read out and loaded into MDR. So that instruction, so the memory unit understood that okay, the value present in the 2000 memory location, that I should transfer back to processor. So in processor way to where I should give, whether it is directly giving to ALU or not, no, that is a data. Actually, the memory will be having an instruction as well as data, so that instruction will be coming from the memory and it will be storing in the next register what we are having, that is called the MDR, that is memory data register. Now, which data I have fetched from the memory? That instruction itself I have fetched from the memory. So that is a data. So that data I am storing in MDR. I told you now that instruction I should execute. So before executing that instruction, I should also make sure that what is IR? IR is the instruction register. The currently executing instruction should be there in your IR register. So what it will do? What should be the next thing? Now the instruction whatever is fetched from the memory unit is present in where? In the MDR. Now I should transfer that instruction into IR register also, because the currently executing instruction is present in the instruction register. I think this is the first set of flows. So at least the instruction we have read from the memory and it has currently available inside the processor. Till now I didn't start executing the program, but this is the initial set of steps. So I will tell you one more time. The program will be there in the memory unit. First I should fetch that corresponding memory address instruction. Assume that my instruction is present in 2000. So the first instruction I should fetch from the memory. The first instruction's address will be storing in program counter. That is the initialization part. Once it was loaded with the program counter, that data will be transferring to your MAR, that is your memory address register. And so that register will be, memory address register content will be transferring to memory unit. So it will get to know what is the address, but whether I should write it to there or I should read from there, the memory unit don't know. So control unit will generate the corresponding signal for that. It will generate a read signal. So memory unit understood that okay, in this corresponding particular memory location's content it should read. Once that instruction is fetched from the memory, it will be storing inside the processor. And where it will be storing? For that we are having another register called memory data register. So that data register that is currently executing instruction, that should available also in the instruction register. So the MDR content will be again copying into IR register. So this is the initial part. After that, what will happen? Now the instruction present in IR register, I should decode that. Who should decode? Processor should decode and execute. Decode means what? What is the operation it is doing and where is the operands present. We know that every instruction will be having two parts. What is the one is opcode. Opcode will be telling about what is the operation I should perform, and operand will be telling where is the data present inside that. So that decode and execution part will be performing in the next step. So what will happen in the decode? Instruction present in, now I have taken the data from memory unit and it is available in my IR register. I am trying to decode it. Decode it by the processor and understand what operation it has to perform. While when it is loaded into IR register itself, already one instruction I have fetched from the memory. Immediately your program counter will be increasing by 1. So it means that it is just next to immediate instruction, it is pointing to the next immediate instruction. So it is incrementing. What is the content of program counter? Initially it was 2000. Now once the 2000 content, once it fetches to the processor, program counter will be increasing to 2001. That is the next instruction where the program counter is having. So the next instruction's address will be loaded with the program counter with the 2001. That is the next step of instruction. After that, if the data required in the operation is available in the register, then it performs the operation. For example, if the initial instruction, whatever was I have shown, is like add R0, R1. if this was the instruction, both R0 and R1 is available inside the processor. There is no need for fetching anything from the memory, so that immediately the ALU can perform the operation. That was the next statement. If the data required for operation, what is the data required for the operation? That is the operands of the instruction R0 and R1. If R0 and R1 is present inside the instruction, then if both are present inside the processor itself, then there is no need of fetching any data from the memory. Immediately the processor can do the operation. If the data is present in the memory, for example, instead of R1, instead of R0, whether the data was present like add, the instruction what I have shown before, like add location A, comma R0. In this case, what will happen? Location A, comma R0, if this is the instruction I am having, in that time, location A is in the memory unit. That is not present inside the processor. R0, R1, R2, all those general purpose registers and all available inside the processor. But location A is coming from the memory unit. So what should I do? I should go to this location A address in the memory, and again what is the operand present inside that location I should fetch and I should take it into the processor. So that is the part. I, are you clear with what I am telling? Are you getting it?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay.
Yes, ma'am.
So R0 and R1 are the operands present inside the instruction, means both will be present inside the processor. So processor can directly execute that instruction. But instead of that, if location A or any particular location, for example 3000 is the location I am giving, so in that time I should fetch the data present in 3000, and that should extract from the memory unit, and I should keep it in any of the general purpose register. So that operation is pending. That is the next point is telling, if data is present in the memory, then some other set of things I should do for fetching the data from the memory to the processor. So what are the things is doing? So I should know where is the data is residing. That is, I already told in my example, that is present in the location A. Location A itself is an address. So I mentioned that it is 3000. So the address of data will be there. Which register can hold the address? MAR only. Only we are having only one register for holding the address of the data. The program counter is already having the value 2001. That is the next instruction it should fetch. So the program counter is already having the value. Its purpose is some other thing. It's not for transferring an address. Your program counter is just for tracking which is the next instruction should execute. So the address of data what I required is my location A, that is 3000. So that I will be transferring to MAR. Once it will get into MAR, that will be anyway memory unit will get it, and that will keep in which bus, through address bus it will connect to the memory unit. After that, so memory unit understood that okay, this is the address, 3000 is the address, that much memory unit understood. But what operation, again memory unit don't know whether I should write into 3000 or I should read from 3000. So that time again the control unit will issue the read signal. So once the 3000 data is fetching from the memory, it will be storing to which register? Already in the same story we have told for instruction. Now the data I am checking. So in 3000 memory location, the value was present is 5. Assume that the value present in 3000 memory location was 5. So that data will be taken and it will be storing in which register? When you fetch the instruction from the memory, it was stored in which register? See, when you first the instruction and read out and loaded into which register?
Memory data register.
Memory data register. In the same way, if you fetch the value present in a particular memory location, for example 3000, that will be loaded into which register? MDR only. It will be loading into MDR. So MDR is present inside the processor. So from memory to processor, that transfer has over. Then few set of ALU can take data directly from MDR. Directly ALU can take the data from MDR, but few set of this processor, the data should be always available in the general purpose registers. So such type of things, from MDR the data will be placing into any of the general purpose registers. So from MDR data can be directly routed into ALU, or it can be placed in the general purpose registers and the operation can be performed. So the operation is performing inside the ALU. Again, the result I should write into the register or even into the memory. The result of the operation can be directed towards the memory or into the registers. Okay. So how can it write the result into the memory? What all are the things? Now where is the data? Data will be processed in the ALU and the result is available and it was written into R0. And after that, if it wants to write into a particular memory location, that address the processor should give it to MAR, and MAR will give that address into the memory unit. But after that, the control unit should issue a write signal, and then that time the data present in R0 will be copying into the corresponding memory location. So result part is result of the operation can be directly write into either register or the memory. So this is all about the execution sequence of the instruction. One more time I will tell. So at least now everyone please listen. So this is the complete structure of the system. So we will have a memory unit, input output unit and a processor. So you are having memory unit means this is for storing the data, and you, instead of taking the data from the memory unit to ALU, actually we are memory unit to ALU, we are having a set of other registers which is residing inside the memory also. So what is the thing it will be doing? The first instruction address will be storing in ALU. From there it will be starting. We are assuming that the instruction is present inside the memory. So instruction is present inside the memory. So the address, the CPU, the processor will be loading into the program counter. So what is where the instruction is residing, that address will be storing in the program counter, assuming that it is in 2000. So program counter is having the value 2000, that will be loaded into MAR. MAR is memory address register. So it will be loading into MAR, and that address will be communicating with the memory unit. When the memory unit knows that corresponding address, the control unit will also generate a read signal, so that the memory unit understood that from this 2000, I should read the data and I should give back to processor unit. So the instruction present in the 2000 memory location will be fetched from the memory and it is storing into MDR. So the data will be storing in MDR, and that data is the instruction present in 2000 memory location, and that complete instruction will be copying into IR register. That is the instruction register, because the currently executing instruction should be there in the instruction register. In the same time, the program counter has already fetched the instruction in the 2000. So the next immediate value will be, the program counter will be increased by 1, and so it will be pointing to 2001. Now the instruction is available in IR register. I should decode and execute the instruction in the IR register. How can I decode and execute the instruction in the IR register? For that, first it will be checking what is the operation it should do. That is performing by the that will be getting from the opcode, and what is the operands. If both the operands or all the operands of the instruction are present in the general purpose register, ALU can directly perform the operation. But if any of the operand is present in the memory, that time ALU should again generate the address of the operand, and it will be keeping in the MAR, and MAR will be keeping the data transferring through the address bus to memory, and the control unit should also generate a read signal a read signal, and then that data will be taken from the memory, and again it is storing into MDR, and that MDR some cases directly can ALU can take data directly from MDR, or some cases it will be transferring to the general purpose register, and then from the general purpose register it is taking the content, and after the calculation the result will be again right back to the general purpose register or even through the memory. For that, control unit again should generate the write signal, and also the ALU should specify where it should write the content. For that, again MAR will be using. So the first part, result part, you can just leave because it was not clearly mentioned in the text. What they are expecting is the result can write into the registers. So up to that, anyway, I think everyone is clear. Program counter will have the first instruction. That address will be storing first instruction's address. That will be storing in MAR. That will be given to memory unit, and at the same time control unit will be generating a read signal, and it will be fetching the data, storing in MDR, and it is transferring to IR. IR will be having the current instruction that will be decoding and executing. When the instruction is having all the operands in the general purpose register, direct execution by ALU. If anyone is not there, any of the operand is not there in the general purpose register, if it is there in the memory, again that data address will be keeping in MAR, read signal will be generating, fetching the data to MDR and transferring to general purpose register, and ALU will be again executing the instruction, and result will be storing into general purpose register. This is the complete operation. Okay, so I will show a video related to that. Maybe that will give you a clear idea. And what we will discuss in our next class is how can you measure the performance of a computer. How can you tell that this computer is better than some other computer? How can you compare the performance of two computers? So that is what we'll be discussing in the next session. Any doubts?
Y and store the result in Z. If I was going to write something similar in an assembly language, I would need more commands. I need to think about the accumulator. So what we're saying here is load the contents of memory location 10 into the accumulator. Add the contents of memory location 11 to whatever's in the accumulator, and then store whatever's in the accumulator back into location 12. Referring to memory addresses by numbers is called direct addressing. Some assembly languages will allow you to use what's called symbolic addresses. So for example, I might say load X, add Y, store Z. That depends on the language. Once my assembly language source code has been turned into machine code, specifically once it's been assembled, it might look something more like this. You can see here we're using 6 bits for the operation code and 10 bits for the operand address. You might find something like this in a very old 16-bit machine. Now let's think about the registers inside the CPU. The blue box shows the CPU, and we can see inside there we've got a control unit, we have the accumulator, and the arithmetic and logic unit. We've also got
Accumulator is also a register present inside the processor. You can just imagine that as general purpose register. Okay. Now you imagine it as general purpose register because our textbook was mentioning it as general purpose thing, general purpose register. So the example, instead of general accumulator, you can think like it is general purpose register.
got some other registers, the program counter, the current instruction register, the memory address register and the memory data register. And we're going to take a look at how these different registers cooperate to run the program. You can see on the right hand side I've got the memory, and the program has already been stored in memory. Now I think we need to take a reality check at this stage. First of all, the accumulator is actually a register which is part of the arithmetic and logic unit. But for the purposes of this demonstration, we've separated them. Secondly, the program wouldn't be stored as assembly code as shown here. It would be the machine code that's inside the RAM. The memory addresses themselves would also be in binary. And to tell you the truth, we'd be numbering from the bottom up. But for the sake of this presentation, we've distorted the reality a little bit. So what happens when a program runs? To begin with, the program counter stores the address of the next instruction to be fetched. In this case, the first instruction, which you can see is in memory location 100. Before we can fetch the instruction from the RAM, that memory address has to be placed into the memory address register. Once this has happened, the contents of that memory address can then be loaded into the memory data register. So we're fetching the first instruction now. Next, that instruction needs to be placed inside the current instruction register. Once it's been fetched into the current instruction register, the program counter will increment by 1. So the program counter is always pointing to the memory address of the next instruction to be fetched before we've even executed this one. Now we can decode the instruction. And without going into detail, the control unit comes into play and it opens various pathways. The next stage in the process is to execute that instruction. The instruction is load 10. In other words, load the contents of memory address 10. So we're going to fetch something from memory address 10. So memory address location 10 now goes into the memory address register. Then we can take the contents of memory location 10 and place that into the memory data register, overwriting its previous contents. And then the contents of that memory address can be placed into the accumulator. That's the first instruction executed. Now we're going to fetch the next instruction. The program counter is already pointing to the memory address of the next instruction, so that memory address can be copied from the program counter into the memory address register. We can then take the contents of that memory location and put it into the memory data register. Now it will move into the current instruction register, ready to be decoded. But before we do that, we increment the program counter, so it's pointing to the next instruction. Okay, so it's time to decode this instruction. So add 11 is passed to the control unit, various pathways are opened, and the control unit makes sense of the instruction. So this instruction says add the contents of memory location 11 to whatever's in the accumulator. So this is where the arithmetic and logic unit really comes into play. An add instruction is passed to the ALU. The contents of the accumulator are moved to another place ready to be worked with. Now we can get the contents of memory location 11, and because we're going to fetch something from the memory, that memory address has to be placed into the memory address register. Once that's happened, we can get the contents of that memory location and place it into the memory data register. You're probably starting to see what the memory address register and the memory data register do. Whenever we want to get something from the RAM, or move something into the RAM, as we'll see in a moment, we must put its memory address into the memory address register. Whenever data, or a program instruction, moves to or from the RAM, it goes via the memory data register. So we have our number 3. That gets placed into the accumulator, and then the arithmetic and logic unit will add that to the 2 that we originally had and place the result back into the accumulator. So we're keeping a running total. It's accumulating the result. It might be worth mentioning at this stage that the circuits inside the arithmetic and logic unit are called adder circuits. They're actually very simple. The truth is, a computer is just a very sophisticated adding machine. Okay, so now we're ready to get the next instruction, which is in location 102. So the memory location 102 is copied into the memory address register. The contents of that memory location, in this case the last instruction, are copied into the memory data register. This instruction moves into the current instruction register. You can probably see what's going to happen next. We increment the program counter. We would probably have a stop or a halt instruction in that position. Now we can decode that instruction, which basically says store the result in the accumulator back into location 12. We're going to put something into location 12, so that memory address must be put into the memory address register. And the contents of the accumulator move via the memory data register into that memory location. And that's our program complete.